I, I hope you enjoyed magnesium burning dry ice as much as I do. But now let's return to some conceptual things, and let's talk about standard enthalpy. And in particular, I want to talk about the standard enthalpy of reaction. So enthalpy, the enthalpy of a reaction is extensive. That is, it depends on how many moles of things I allow to react. But to facilitate tabulation, I would like to have some sort of standard and one that is intensive. And so the International Union of Pure and Applied Chemists, that's IUPAC, has created the standard enthalpy of reaction, which is an intensive quantity. And that little superscript on the H, superscript O, that I've highlighted here with a little blue arrow, that has implications. It refers to a standard state. So in particular, it implies 1 mole of a specified reagent and all reactants and products in their standard states at a given temperature. So you would tabulate these as a function of temperature. Standard states are chosen by convention. So for example, for a gas, it might be a pressure of 1 bar. That would constitute the standard state of the gas. You would measure it if you could at that standard state. So just to give you an example then, a reaction we've seen previously, carbon reacting with oxygen in order to give carbon dioxide gas has a standard enthalpy of reaction of minus 393.5 kilojoules per mole. Up till now, I have not had per mole on enthalpies of reaction. But here, because the standard is to react 1 mole, and so in particular, we're taking 1 mole of carbon being combusted. So you've got to specify which thing is going to be the 1 mole. And we're working at a specific temperature. In this case, it's implicitly 298 Kelvin. It doesn't have to be, but that's quite typical, room temperature. And it's an intensive quantity because it specifies per mole. So the number is not allowed to vary anymore. This quantity is tied to a specific number, Avogadro's number of carbon atoms. So in that case, given that I now have the intensive property, if I were interested indeed in 2 moles of carbon reacting with 2 moles of oxygen to make 2 moles of carbon dioxide, what would the heat of reaction for that be? Well, it would be twice the standard heat of reaction, because the standard heat of reaction is for 1 mole. And so it would be minus 787 kilojoules, twice this value, and no longer with the per mole appearing, because now we're talking about an extensive heat of reaction. Another terribly useful standard quantity is the standard molar enthalpy of formation. And so that's the standard enthalpy of reaction to form 1 mole of a substance from its constituent elements in their naturally occurring pure elemental forms. That defines the standard molar enthalpy of formation. And so again, that superscript indicates that all the reactants and products are going to be found in their standard states. And it's most helpful maybe to just offer an example of what that means. Let's say I'm interested in the standard molar enthalpy of formation of liquid water. And I've chosen liquid water because its standard state at 298 Kelvin and 1 bar pressure would be as a liquid. That's how it exists at room temperature. It is formed, its constituent elements are hydrogen and oxygen, and in their most abundant forms at room temperature and 1 bar, that would be hydrogen gas and oxygen gas. So that reaction can be measured at room temperature. It has a heat of reaction of minus 285.8 kilojoules per mole. That's intensive because it's per mole, and that defines the heat of formation of liquid water. Another way to put that is that 1 mole of liquid water is 285.8 kilojoules downhill from its constituent elements in their standard states at the measured temperature. So we're going to see a few abbreviations on enthalpy. We've already used a few. I just want to round out the pack here. VAP is vaporization or evaporation. That's the phase change from liquid to gas. Sublimation is the phase change from solid to gas, which can occur under certain pressure conditions. FUS is fusion, that's melting, or the reverse process obviously is freezing. TRS is a general transition between phases where you're not really specifying whether it's vaporization, sublimation, or fusion. Mix refers to mixing. We will get into quantities that are associated with mixing in not too long. Sometimes you'll see ADS, adsorption. That is making contact, say, with a surface of something, a gas coming into contact with a surface, a solid. C for combustion, F we've already seen for formation, and R we've already seen for reaction. So elemental heats of formation, to assign specific values for heats of formation, we need to have heats of formation for the elements themselves, because they're what's being used to make other molecules that are not elementally pure. And so in order to set a 0, the convention is that the heat of formation, the standard heat of formation for a pure element in its most stable form at 1 bar and the temperature of interest is 0. Right? So that's pretty simple. That's by definition. We will call that 0. And since we will make all other molecules out of the constituent elements, the enthalpy change involved in creating those molecules is the heat of formation of the molecules, because the enthalpy of all the starting materials is 0. So just a quick tabulation then, at 298 Kelvin, the heat of formation of molecular hydrogen gas, 1 bar pressure, 0. Of molecular oxygen, 0. Of molecular chlorine, 0. Of molecular bromine, 30.907 kilojoules per mole. Iodine, 62.438 kilojoules per mole. And carbon, in its diamond form, a rather nice form, 1.897 kilojoules per mole. And if you're looking at that and thinking, 0, 0, 0, not 0, not 0, not 0. But these are pure elements, so what's going on there? These are pure elements, but that is not their most stable form at room temperature, 298 Kelvin, and 1 bar pressure. So bromine is a liquid by preference at that temperature and pressure. Iodine is a solid, although it's one that's got a lot of gas vaporizing above it, but still the solid is the most stable form. And finally, diamond, alas, is not the most stable form of carbon. Would that it were. We would live in a very beautiful world. Graphite is the most stable form of carbon, and you need to press on it hard to make diamond. You remember Superman used to do that in comic books, but that's probably before many of your times. What are these heats of formation useful for? They are useful for getting heats of reaction, because I can take advantage of Hess's law to add and subtract things in order to look up tabulated heats of formation and plug molecules into equations and come up with heats of reaction. Let me show an example. A generic example. A moles of A plus B moles of B goes to Y moles of Y plus Z moles of Z, whatever molecules A, B, Y, and Z might be. And so if you added and subtracted the relevant reactions, because they could all trace back to the same original elements, which define 0. And so I would need A times the heat of formation of all my molecules A, plus B, because there's B moles of them, times the molar heat of formation of my molecule B, going to Y times the heat of formation of Y plus Z times the heat of formation for Z. So number of moles here, because that'll dictate the total enthalpy. And here's the per mole enthalpy in that molecule. And you get a terrifically simple expression. The heat of reaction is equal to the total heat of formation of the products minus the total heat of formation of the reactants. That is, I'll just expand it out, Y times Y plus Z times Z minus A times A plus B times B. So if you've got a bunch of tabulated heats of formation, it's a question of flipping through that tabulation, or scrolling, I suppose, if it's online, finding the relevant numbers and plugging them in. Now, what about heats of reaction at different temperatures? So presumably I'm not going to tabulate heats of formation for millions of substances at 297 Kelvin and 298 Kelvin and 299 Kelvin. That would be unpleasant. What I can do in order to learn about different temperatures, let's say I want to go from room temperature, that's a typical one, that'll be my T1, to T2. Well, how do I get a change in enthalpy when I change temperatures? I integrate the heat capacity. So I've got a temperature at which I'd like to know the heat of reaction, because it's a state function, the path doesn't matter. So what I can do is follow this path, cool my substance down, my reactants down from T2 to T1, react them at T1, or look up the known reaction at T1, warm them back up to T2, the products in this case, and that path is the same as this path, so this heat of reaction is equal to the sum of the enthalpy changes along those three paths. So first path is minus the integral from T1 to T2. I'm going from 2 to 1, but I'll take the negative of the integral, and so I can go from T1 to T2. And you'll see why I want to do that in a second. The heat capacity of the reactants. Delta H along this second path is just the heat of reaction at that reference temperature, which hopefully I already know, or I can look up in a standard tabulation. And then the warming up is, again, integration of heat capacity. And so when I sum these together, and that's why I want to have the same limits on these two integrals, it's the heat of reaction at the reference temperature plus the integral from T1 to T2, heat capacity of the products minus heat capacity of the reactants. So now, instead of having to tabulate heats of formation, for instance, at zillions of different temperatures, I only tabulate them at one or perhaps a small number of temperatures. And if I also tabulate heat capacities, and if those heat capacities are not themselves strong functions of temperature, you could, of course, tabulate them as functions of temperature if you have enough data, you'll be able to accomplish these thermochemical cycles and compute heats of reaction at any temperature of interest. Well, we built a lot of tools this week, and it was actually kind of a long week. Lots and lots of concepts, internal energy, PV work, enthalpy, heat capacity. We've pretty much wrapped those concepts up. So the last lecture of the week that follows this will be a review, and then we'll move on to the next phase of thermodynamics.